Good day, ladies and gentlemen. In this section, we're going to look at the relationship between the hydrocyclone and the milling circuit. We're going to look at high-level basic information and then looking at factors that can influence the performance of this unit. I'll be looking at cyclone basics, factors affecting the hydrocyclone performance, open circuit milling, closed circuit optimization, followed by circuit checks, and then general guidelines. So looking at the cyclone basics, the hydrocyclone is consisting of an inlet, vortex finder, and spigot. So particles enter the inlet, starts rotating, and we then get a finer fraction that's reporting to the overflow, and a coarser fraction reporting then to the underflow. Factors that's affecting the hydrocyclone performance. In the client's mind, the separation needs to be perfect. Unfortunately, that's not the case. You have some short circuiting of coarse particles to the overflow and some fine particles to the underflow. The coarse particles that's reporting to the overflow happens as the feed enters the inlet of the cyclone. A portion of the material stays on the roof or the top of the cyclone, and then it moves down next to the vortex finder and it escapes. There seems to be a boundary layer next to the vortex finder that has got a downward movement and that's not rotating or participating in the classification process. In terms of the fines that's reporting to the underflow is always wet. You cannot have no water in the underflow because the water drags down with the solids, and you need the water to form a lubrication. So whenever there's water in the underflow, there will always be fines reporting with the water. The objective is to have as little as possible water in the underflow. There's also then fine particles that gets into the cyclone and it stays on the side of the hydrocyclone, on the outside wall. Now, in classification, it's a balance of two forces, a drag force that's trying to pull the particle to the center and through the overflow, and then a centrifugal force, forcing the particle to the outside. Whichever force is the strongest, that's the direction the particle will flow. However, if the fine particle sits on the outside, then there's only essentially one force applicable, and that's a centrifugal force, because there's no water behind the fine particle to initiate movement. So we have also fine particles that does not have both forces applicable on it, as well as a possible entrapment. Looking at the hydrocyclone efficiency, ideal separation is represented by this blue line. The red line is illustrating the actual separation. And the shaded areas are then material that's misplaced in the wrong direction. You will see on this section here, that curve does not go through zero. A portion of the fines being misplaced to the underflow is a function of the alpha water or bypass water. When we are looking at the efficiency of a hydrocyclone, we have to look at all the particles that participated in the classification process. It means we have to discount the fines that got dragged out to the underflow of the alpha water. And we then get to the corrected curve, which is then this yellow curve. We then have a D50 actual cut point and a D50 corrected. And in literature, you will see the description D50 with a subscript C. That C refers then to the corrected curve. The tromp curve is therefore defined by three parameters: the cut point, the D50C, Then the alpha water that's dragging the fines to the underflow. And this formula or this relationship, the calculation of the alpha water is very important. If you look at this description, it says that the alpha water is a function or is equal to water in the underflow divided by water in the feed. So we want as little as possible water in the underflow, but as much as possible water in the feed. Then we've got minimal alpha water, the lowest alpha water ratio. Imperfection is the slope of the separation curve. So when we look then at the corrected curve, we can then see that the 3 points, the D25, D15, D75 points are used then to calculate the slope. The D25, D15, D75 is the percentage recovery to underflow. Alpha water, or the bypass water, as we then start to increase or reduce the alpha water by increasing the feed density, we can sharpen up on the separation curve. And as mentioned, we make the spigot as small as possible to minimize the amount of water reporting to the underflow, and we increase the feed dilution. And there lies the problem. We can't make the spigot too small because the cyclone will start to roll. We can't add too much water because that water reports the process following the mill circuit and may not be, that additional water may not be beneficial. So it's a balance that we have to take into account. When we look, we've looked at the corrected curve, but in reality, the red curve is what is happening in the mill circuit. There is going to be misplacement, of course, and fines, but then there's the amount of fines being misplaced by the bypass water. So we as suppliers need to look at or recommend the best conditions to make the curve as steep as possible, but also keep the bypass water as low as possible. Moving on to the open circuit milling. In open circuit milling, the feed enters the cyclone, underflow through the mill, overflow bypasses the mill, combined in the mill discharge sump, and it moves then onward to the next process. So there's not much on this open circuit milling around the cyclone that is too complicated. If we make the vortex finder smaller, we change the mass split. We can change the percent or the fineness in the overflow, so it behaves like a normal hydrocyclone. When we select cyclones in these applications, we make sure that the overflow is finer than the grind being produced by the mill circuit, so that we do not bypass material that should have got milled before to increase liberation for the next process. One thing to note, if water is added in the mill discharge sump, rather add the water to the feed to the cyclone. That reduces the feed density, it increases separation efficiency, and you do not disturb your water balance. Closed circuit milling, that is what the circuit looks like. You have feed coming into the mill. Mill discharge reporting to the mill to the cyclone feed, cyclone underflow back to the mill, and the overflow leaves the circuit. Very important to understand. In this section here, see it as a black box. So there is a stream crossing the border, F80, work index, F1 to F8, and the tons per hour. And then you've got your PID leaving the circuit. The question, when there is misplacement from a mill cyclone overflow, or when the relationship between the cyclone and the mill is getting out of sync. In other words, most of the times the grind is becoming too coarse, or there's too much coarse material in the overflow. Clients want to go to smaller cyclones. Why is that? If you think of open circuit milling of a normal hydrocyclone, smaller cyclones do cut finer. But in the milling circuits, things are slightly different. So here's an example of everything being identical, except for the cyclone diameters. One has got a large cyclone and one has got a small cyclone. And then we've got water addition in the circuit. And for this example, we're running on level control. The question then is, how would these two circuits differ from each other in terms of the cyclone cut point, the circulating load, misplacement to the overflow, and the PAT of the grind? On the cyclone cut point, when you ask people how would it be different between the two cyclones, the answer is normally the bigger cyclone have a coarser cut point, and that is correct. Secondly, the circulating load. Which one of these two circuits would have the higher circulating load? Most of the times, people would think the larger cyclone will have the larger circulating load because it's a bigger cyclone, there's more volume being pumped around. Fortunately, that's not the case. It's the smaller cyclone. Then misplacement to the overflow. Which one would have most misplacement? Again, the answer normally the bigger cyclone because the centrifugal forces on smaller cyclones is higher. In this case, again, the smaller cyclone will have more misplaced material. And then the question about the grind would be similar. So looking then at the circulating load, why is the circulating load higher on the small cyclone? Well, as the material gets into the mill, the cyclone is trying to send the material back to the mill. The circulating load starts to increase. The material report back to the cyclone and it continues sending it back to the mill until the feed density to the smaller cyclone has increased to such an extent that your cut point is starting to become coarser. On the large cyclone, because of the coarse cut point, it has removed material faster than what's entering into the circuit. So now we are starting to reduce the circulating load and we have to add water to maintain the level in the sump. And there the feed density starts to reduce. And that results in the cyclone with the larger diameter cyclone with the coarse cut point to become finer. That is then the relationship between the feed concentration solids on the x-axis and then the cut point correction factor. And we can see as the feed solids concentration increase, the cut point increases. So looking at a small cyclone to improve a situation on a mill circuit, which is the result of something else, is dangerous. And it may actually just backfire and produce the opposite effect. In terms of the grind, why is the grind similar? Coming back to this picture here, if you look at the equation on the top, bond equation, it's a combination of the work index, the tons per hour, PAT, FAT, and then some efficiency factors. Nowhere in that equation is there anything about the cyclone. So the cyclone cannot change the grind or the PAT. Some of you may frown upon that, say that something is not right. And I'll get to that discussion just now. When suppliers are given information to select mill cyclones, we are given a mass balance. So first of all, when you need to look at the overall grinding process, one needs to see how much energy is being introduced into the process. We as suppliers are getting then the mass balance of the feed, overflow and underflow of that cyclone, and we do a simulation. And then the mill supplier on his side is doing then a separate simulation to calculate what size of mill it is. The simulations are detached. To my knowledge, I'm not aware of a simulation program, but I could be wrong, that is combining the cyclone and the mill on a continuous evaluation state. If the size distribution gets into the mole has got a certain breakage function. If you then go to the cyclone will produce a certain size distribution back to the mole. Now the feed size to the mole has changed, and the breakage size distribution needs to be re-altered or recalculated. This is a very complex calculation process. So most of the applications that we as suppliers are involved in revolves about getting a mass balance and selecting the cyclone. And in that mass balance, the grind has already been specified. So we are using that as our reference. Now, coming back to the cyclone itself and the grind. There are two inputs into this milling circuit, energy and ore. There's an output of this milling circuit, and that's the production rate of the fines. There are two actions taking place, the grinding of the coarse material and the removal of fine material. So essentially, there are two efficiencies, a grinding environment efficiency and a classification system efficiency. So when we start looking then at this circuit output, it's a function of input and efficiency. Input function relates to more power draw and the grindability of the ore. Efficiency relates to classification system efficiency and ball mill grinding rate efficiency. We can then recombine the mill power draw and classification system efficiency. Look at the effective mill power draw. In other words, what amount of energy are really being used effectively. And then ore grindability and ball mill grinding rate efficiency combines to form the ball mill specific grinding rate. And then the combination of these two gives you the circuit output again. It's just to show you on high level a relationship. What is important then is that the circuit output is a function of the ball mill power, classification system efficiency, ore grindability, and ball mill grinding efficiency. And here comes the cyclone aspect in. So the cyclone do play a role to a certain extent, but there are other factors as well. So what is the impact then of circulating load on the process? If you had a perfect classifier, then you would have the mill efficiency follow this trajectory. As the circulating load increases, the mill efficiency will increase because higher circulating load results in a reduced retention time and you utilize your energy then more effectively. But that is when you had the perfect classifier. Unfortunately, that's not the case. What is shown on the picture on the left-hand side is that as you increase your efficiency of separation or classification, one can impact on the throughput through the mill. So classification, efficiency do play a role on the mill circuit. But let's continue. Increased circulating load versus classifier efficiency. It's got an opposite trend. As the circulating load starts to increase, our efficiency declines. And that is shown by the graph on the left-hand side. So there is a balance. This increase in circulating load also impacts on the efficiency of the hydrocyclone. The higher the feed solids concentration, the shallower the curve. Our aim is to have the curve as steep as possible. Classification efficiency, which was mentioned on the previous slide, is defined as the tons per hour in the overflow at a 95% passing size. In other words, you look at the overflow size distribution, look at the 95% passing size, and say, okay, at that size fraction, what is my percentage in the feed? And then you calculate the tons in the overflow and the tons in the underflow. So in this block, the tons per hour in the feed to the cyclone on the right-hand side is 100 tons. Overflow is 28, underflow is 72. So we would take 95% of 28 tons divided by 52% of 100 tons. And that gives you your classification efficiency. Coming back then to the combination of the mill efficiency and the classifier efficiency. When you combine these two curves, you get an optimum. And that is the purpose of the hydrocyclone. It needs to maintain the circulating load in an optimum range, where the mill is partially happy and the cyclone is partially happy. If you operate at a low circulating load, the cyclone works effective, but the mill is not utilized correctly. And vice versa. If we go to too high circulating loads, classification efficiency falls off. And that's what happens more regularly these days. People are increasing tonnages, circulating loads are increasing, the cyclones are becoming less efficient, and then we want to make a change to the cyclone to improve the efficiency, while the problem lies somewhere else. When we have to select cyclones, we are given a PAT. As mentioned before, that is coming from the supplier or from the engineering house, and it specifies the grind as a PAT, but that is on the overflow of the cyclone, because that's a stream leaving the milling process. We as suppliers are using this red line. That is our efficiency curve, and the D50C, the cut point, is our reference. So we need to move from one curve to another curve, and we do that by applying a correction factor. So that is how we select milling cyclones. Obviously, there's the throughput, the number of cyclones, but the point to be made here is there's a relationship between the cut point of the cyclone and the overflow. Often people would ask, why is my cut point coarser than my grind? And unless you understand these set of graphs, it's very difficult then to explain to the client. They are separate curves. So if you want to install a cyclone with a finer cut point, it's going to try and move the overflow to a finer fraction as well. The mill circuit won't allow that, and you're making things worse. So in a closed circuit milling application, the water into the process, stream 5, is dictated by what is the overflow density that can be tolerated by the processes downstream. The cyclone cut point influences the circulating load and not the overflow size distribution. Feed solids concentration to the cyclone is influenced by the circulating load and the water addition to the circuit. You have high density applications. Apologies. You have high density applications. In other words, overflow density going to leach at a density of 135 or 1.40. It means you cannot add too much water in the process. But in that same application, the client wants to operate at circulating loads of 350 or 400%. So you have a high amount of solids being recirculating, but the amount of water is quite limited because it's going to influence the process downstream. One option is to look at dewatering cyclones on the mill cyclone overflow. You can add more water in the process, you dilute the feed to the primary cyclone, and the dewatering cyclones underflow will move to the next process. The overflow water can be returned back into the process, into the mill circuit. However, this type of design is not suitable where you have a high clay content or very fine grind. It's maybe advisable, if you consider this type of design, to make provision for a bleed off in case there's too much fines that is building up in the circuit. But this type of system is something to consider if you want to improve your classification efficiency. The cyclone has got two shortcomings. At very coarse grinds, a screen is the better option. However, there are situations where clients still want to use cyclones, and then the cyclone is starting to operate outside its design conditions. It doesn't mean it cannot operate there, but it's not that efficient. And then multi-density material. Milling circuits with multi-density material is also a challenge for the cyclone. A screen is again a better option, but there are situations where clients want to stay with cyclones, and then again, we as suppliers have to look at what options are to our disposal to optimize the cyclone or this design as effectively as possible. keeping in mind it will not be as efficient as when it was a homogeneous type of material. Vertical cyclones. Cyclones can be installed in a vertical position, but you have a lot of feed tonnage or a lot of pressure that's impacting on the spigot because the whole cyclone is full of liquid. So you need to make your spigot diameter as small as possible. That makes it very difficult if you've got fluctuating circulating loads because there's not enough room in the spigot to accommodate the fluctuating tonnages that's been generated. Inclined cyclones that's lying on its side. Because its cyclones is on its side, we can install larger spigots. It results in less wear of the spigot. The cut point is slightly coarser. So if you are operating a low density environment, the efficiency of an inclined and a vertical cyclone very similar, but if you go to a high density circuit, your vertical cyclone would be the better option. Flat bottom cyclones, these are cyclones that's used when we are going outside the size range for a conical cyclone. But we may be too fine for a screen application. So flat bottom cyclones cuts coarser, but the efficiency is slightly poorer than that of a conical unit. It is, however, not easy to rope. And if you've got multi-density material, you may enter, we may enter a situation where there is a buildup of high-density material at the bottom end of the cyclone, and that can then be the initial stages of a possible dense medium effect. The flat bottom cyclone is therefore used for specific applications only. Two-stage cyclone application, where the primary cyclone overflow would go then into a secondary cyclone. So on the picture on the right-hand side, cyclone on the top of the plant, the primary cyclone, gravity feeds then to the secondary cyclone. This application is used where you want to sculpt off misplaced material from the primary cyclone, but it works well in low density circuits. So the overflow of the secondary cyclone must be going to a thickener. If it's going to leach, you have a problem because your primary cyclone is not going to be that efficient anymore. Dewatering cyclones, small diameter cyclones, cut point in the region of about 12 microns. In some cases, it can displace or it can substitute thickeners. However, the water will never be clean. And we have to therefore be quite careful that we don't mislead clients. It has been used in the past, but there wasn't a lot of fines present. It is something to consider due to the lower capital operating cost, but just bear in mind, you won't get very clean water to the same quality as that of a thickener. If you want that, a thickener is your best option. Moving to closed circuit optimization. So we've seen now that there's a black box and there's factors influencing the performance of the cyclone and the mill. There's a relationship between the grind and the cut point of the cyclone. We want the slope of the overflow size distribution as steep as possible. And there's an optimum range in terms of circulating loads. The effect of the cut point we've discussed when we looked at the large and the smaller cyclone. We know now that the smaller cyclone are not always the better option. The effect of circulating load we've discussed, and we want to maintain the circulating load between optimum range, roughly about 150 to about 400%. Then control philosophy is another aspect that influences the performance of the cyclone. In this situation for plant up in Africa, they had a situation where the leaching tanks were starting to sand up. The black line is the pressure on the cyclone. The purple line is the sump level, normal discharge sump level. And then the red line is the power from the pump. So as the sump level started to fluctuate, the pump will have situations where it's speeding up and then it will overload the capability of the mill cyclone. The cyclone will start to rope and will send coarse material to the overflow. You can open up another cyclone, but later then you have to close another cyclone. So the question was, or the clients requested, to look at alternative cyclone configurations or alternative cyclones to get out of this coarse misplacement. So the focus was on the efficiency of the cyclone. But when asked about the mill discharge sump level fluctuations, it turned out there's a flotation process up front, and that oscillating level is coming from the flotation. The suggestion was made to run the pump in a manual mode to take care of the fluctuations, and that is the type of pressure fluctuations that was experienced in the bottom graph on the cyclones after the modification was made. Another example where a client requested assistance for looking at a cyclone that's producing too much coarse material in the overflow. One can see that at one stage it was behaving fairly acceptably. So the client wanted to know what he can do around the cyclone. My request to him was, please provide me with more information, and one of the sets of information was the circulating load. When I looked at the circulating load, I realized the circulating load has increased quite substantially. And if you look at the left-hand axis, reaching values up to 900%. So the cyclone is being fed with unoptimized feed conditions, and therefore it's starting to misplace coarse material. So the cyclone is not the focus point. The focus point is, why is the mill generating these higher circulating loads? Another example where clients has got a cyclone that performed fairly well over time, and then efficiency starts to deteriorate in the cyclone, or something in the process has changed. You get in this orange curve. Clients then often request smaller cyclones. And when you start interrogating why smaller cyclones, it turns out they want a cyclone that will cut fine enough so that it will again get to the original amount of coarse misplaced particles. But when you look at this gray curve, you will find that the P80 is different. And that comes back to the question, why would the cyclone produce that finer overflow? It can't, because it means the grind needs to be finer. When you're doing simulations, it doesn't show you that you are producing a finer grind. It will just give you the size distributions and the client will be very happy. So this type of situation will also not happen. And it comes back to the milling circuit that is an energy function, not the cyclone. Again, we are talking about the two efficiencies, as well as the ball mill power and the ore grindability. If you want to optimize then, ball mill power draw, look at the volumetric ball loading, mill speed, grinding media, discharge design, water usage. That's on the power draw. There comes the cyclone. Water usage, circulating load, multi-stage cyclones, using high efficiency classifiers, ball mill, discharge design, water usage. That is only the cyclone areas that we can focus on. The rest is around the mill, ball mill. Ball mill grinding efficiency, water usage, grinding media sizing, the type of material for the grinding media and the shape, and the ball mill discharge design. So when you want to optimize your milling circuit, the cyclone is only one part of a bigger process, but most of the work actually lies with the mill. Some circuit checks, sampling, using slurry sampling, using a Marcy scale and a beaker. Make sure the scale is calibrated and take the sample properly. If you take the sample, the Marcy Bekker sample, and you have to walk towards the Marcy scale before, and then you release your fingers around the hole to drain the beaker to the right level, you're doing it wrong because the solids has already started to settle out. You take the sample with the Marcy Bekker, get it to the right level, close the holes, walk to the Marcy scale, and get the density. Where do we want to sample? Feed to the cyclone, underflow, and overflow. Now, often clients say, well, we can sample the overflow and underflow, but we can't sample the feed. On most of the cyclones, we can look at an option like this, a branch where you have a pressure gauge and a valve. So if you've got a pressure gauge adapter before the feed to the cyclone, we can modify that, or it can be modified by the mine to have two offtakes, one for the pressure gauge and then one for a sampling point. On the Multotec cyclone, that is an area where we can install this, or you can install that, and that can serve as a sampling point for the feed. Granted, it's not 100% correct, but we just want to get a process indication of what's happening in the process. Accuracy of the samples. We require often 2 or 3 sets of data, and clients do not always understand why. It's because the data that we sometimes get is all over, or it could be biased. Also, it could be imprecise, and obviously that is what we're looking for, getting precise information. So why is this important? We need data to analyze the performance of the hydrocyclone. But that data can also give us an indication what's happening with the circulating load and give us an indication around maybe if there's problems on the milling circuit itself. But if the data is not accurate and consistent, our conclusions may be wrong. When we've got the overflow, underflow, and feed density, so we've got the solids density, the calculations on the grey blocks is what we use, and we can calculate then a mass balance around the cyclone and get into the circulating load. If there's a pressure gauge, we can make a quite accurate assumption of the volumetric flow rate into the cyclone. Having the feed density, we know what tons goes into the cyclone. Having the mass split, we know how much tons goes to the underflow and how much goes to the overflow. Being able to inspect the spigot visually, very important. This is the too wet underflow. There's roping. That's a good discharge. That also helps to optimize the process. If we need to do a mass balance, the information that we would require, at least the minimum information, the feed tons to the mill circuit, overflow density, the circulating load of the circuit, feed density of the solids in the feed stream, and then in the underflow. With this information, we can then construct a mass balance, and obviously the particle density is also important, the type of material that's been processed. When we've got this mass balance, we can calculate the amount of water that is in the feed to the cyclone and the underflow of the cyclone, and we can look at the bypass water. And that's another indicator then if the circuit is operating well or not. And then looking at the size distributions, we would use it in our simulation program and compare it then to the simulated data. We will compare the actual and the simulated data, see how it compares, and if there are deviations, we will then need to investigate it further. And then whatever trends are being obtained by the mine, that also will help the supplier to look at possible causes that is problematic in your process. So general guidelines, install a pressure gauge, very important. Check the spigot diameter, check the discharge for blockages. Check the cyclone internally. Don't assume the cyclone will run forever. It does wear. And once it starts wearing, it can misplace material. Check the feed conditions, and then look, and then the option of alternative wear materials. That is always something that can be to the benefit of our clients. On the hydrocyclones or Multotec, there's weep-holes as well. The purpose of that unit is to indicate when the liner is starting to wear, to take preventative action and replace the liners. Just some useful information. Then, in conclusion, the hydrocyclone cannot change the grind. I trust you will now understand. The cyclone and the mill forms that relationship. Both units needs to be understood. Pump, sump, and instrumentations, all important, all contribute to optimize the unit, but they must be working also in a working condition and a calibrated condition. Getting proper information and the correct information, sometimes one of the biggest challenges that we as suppliers face, because we need to now give you as the client an answer. And if the data is inconsistent, we can't give you the right answer. So we need correct data. And lastly, we can assist. If there is some questions, feel free to ask. If we don't know, we will tell we don't know and we'll find the right people. Thank you very much.